Okay, with that out of the way, let's talk about arrays. And arrays are either the simplest complex data type or the most complex primitive. And the reason why I say this is because arrays are sort of available regardless of the language and regardless of the paradigm. And you'll see why more in a few minutes. But question number one is, what are arrays? Like, definitionally. And we can think of an array as a statically sized, indexable, contiguous block of memory. So let's break this down. Okay. So the first thing is contiguous. What's contiguous? Well, contiguous means that blocks are up against each other with no gaps between them, like so. Okay. And sometimes you'll see people draw this vertically. I prefer drawing it horizontally. Either way, it ends up looking like a ladder or train tracks or something. And you've probably heard the word contiguous before, like the contiguous 48 states, the lower 48 states, right? They're all next to each other. They're all adjacent, as opposed to Alaska and Hawaii, which are disconnected. They're not continuous. Continuous is incorrect because it sort of implies that either it goes on infinitely in both directions, right, like a line, or it can be subdivided infinitely. Think of the amount of numbers between 0 and 1. There's a half, there's a quarter, there's the square root of 2 over 10, there's pi divided by 1,000, right? An uncountable number of numbers are between 0 and 1. So saying that memory is continuous, no one's ever going to call you out on that. In fact, most people won't even notice. But that's incorrect because we can't subdivide memory. So this is important, right? A block is a block. And then we have indexable. What's indexable means? Well, it means that we can refer to a number independently and numerically. And numbers start at 0 and they go up to the number of slots minus 1, right? So this array has 11 slots. So that means that it's indexes or indices, and both terms are valid. And I will switch between them because I do, and I don't know why. But it has indexes or indices of 0 to 10, summing to 11 slots. And then the last thing is statically sized. Statically sized means you can't change the memory once it's allocated. Once we have this block of memory, once we have this block of 11 slots, that's all we have, right? And if we want to make a new array that's twice as large, if we run out of room in this array, we're going to have to create a wholly new array of say 22 elements if we want to double the size, and then copy the elements over and destroy the old array. There's no way once we've run out of room to say, hey, add slots. Okay. And I know some of you are thinking, well, what about a Python list, a dynamic array? And that's a magic trick. There's some smoke and mirrors that Python does to make that happen. And we will talk about that some later on. We'll show you how that gets done. But it's not really adding slots, not the way that you think. And at its core, behind the scenes, this is what's happening. So as a quick thought experiment, what is the largest array that we can have that is physically part of every computer? Put another way, what is a component of a computer that you can think of as just one big array of memory? And the answer is actually in the definition, right? Main memory is one giant array. When you deal with memory in something like assembler, all you're doing is indexing different chunks of memory. All you're doing is referencing different aspects. So on a basic level, memory is just one gigantic array that you're subdividing into smaller byte sizes to be convenient for you. Okay. So then how do we access memory? What's the process of accessing memory? And you're going to see, what does that have to do with arrays? It's actually the thing that has to do with arrays. Okay. We need to remember that each memory address is 1 byte, no matter what. Okay. So moving up one memory address is moving 1 byte up in memory. But in Python, everything is an object. So that means that we're storing a reference at the address where our memory is. Take 2. At the address of our variable or a slot in an array. So if we have an array of data in Python, it looks like this. Right? The thing at index 0 isn't really at index 0. It's a reference to where that thing is out in memory somewhere else. Who knows? It could be higher in memory. It could be lower in memory. Then at index 1, the same thing. Then at index 2, the same thing. So everything in the array itself, everything in the array itself is just a reference to where the main object is. Okay. We need one more big fact before we can get to how do we access stuff in an array at a very low level. We need to get to memory itself. Right? Memory is sometimes called RAM. What's that acronym mean? Random access memory. Random access. So like it kind of jumps all over the place. You don't know where it's going to go? Well, sort of. That's the net result, but that's not what random means in this sense. Okay? Random in this sense is the opposite of sequential access, which is the kind of memory that early computers had. So if you want to think about the kind of memory that very, very early computers had, imagine magnetic tape. Imagine we're at the very, very beginning of the tape and we want to get to the 10th piece of data in the tape. Well, if we want to do that, we have to physically move from index 0 to index 10. We have to move past 1 through 9. And that's very slow. As opposed to random access, you jump to any address instantly. This is a critical fact. Okay, this is critical. Random access memory, if we give it an address, it goes there functionally instantaneously. Okay. Big O of 1 fast, and a fast big O of 1 fast. So, okay. Then in Python, we know how big each slot is, right? Because it's a memory reference. And so for those of you who know architecture, you know that you have either a 32-bit or a 64-bit machine, okay? That tells you the amount of data that your processor can process in one chunk, but also the amount of memory. I'm sorry, take 2. The amount of bits needed to address main memory. So in order to fully address main memory in a 32-bit machine, 32 bits are allocated. So that means our references are 32 bits long. And in a 64-bit machine, it's 64 bits, or 4 bytes, 8 bytes if we convert it to bytes. Remember, 8 bits in a byte. And if that's the case, our slot, the address of the element in memory in an array is real easy to calculate. Our final address here is the base of the array address plus the size of the object times the index. So let's consider some things. Let's do a hypothetical example. What's the one index that every array is going to have? It's going to have 0, right? Every array with any slots is going to have 0. So let's put the 0 in here. We put the 0 in here, and what happens to this section? It gets negated. So the net result is that the data is just at the array's base address, right? So there's two effects here. One, there's two demonstrations. One, this shows you how memory efficient an array is. There is no fat on this data structure, right? We don't need all this additional stuff. It's just, hey, okay, our data starts at the beginning of our array. And on top of that, indexing any spot in memory is really, really, really fast. And computers are just really fancy calculators. So running this equation is also really, really fast. So if you get nothing else from this class on a theoretical data structure point, take that arrays, because of this, arrays are very efficient when it comes to memory consumption and very efficient when it comes to accessing elements of the array.